This is progress podcast number 122, and today we're finishing off the series in the effects of boundary layer shapes and heights on the performance of the boundary layer and the drag of an object. So in the first podcast, 121, we looked at more the pressure coefficient and the general development of the boundary layer and how boundary layer trips work. In this podcast, we're going to be finishing off how the boundary layer trips affect the forces. So if you haven't listened to the first podcast, 121, check that out. And let's continue. So we'll be looking at the same paper called Comparative Study on the Aerodynamic Performance of Airfoils with Boundary Layer Trips of Various Geometric Shapes. And this is open access again, so you can find it in the link in the description. So let's continue here with the effects of these boundary layer trips on the aerodynamic performance analysis. So just as a reminder, we have an airfoil, which is a baseline one that has no trip on it. Then we have three different types of trips. We have a rectangular one, which is effectively just a box. Like if you have a regular surface, then you have just this box popping up over the top, and it's of various heights. It goes from like 0.3 millimeters up. We then also have a right angle triangle. So if you have the regular surface, then you just have like this fin kind of coming up and the free stream velocity coming at it. Then we have the isosceles triangle, which is again, you have the surface, and now you have just like this nice little ramp with a peak at the top. And both of these sides are the same length. I just drew it a little bit dodgy. But anyway, they're the three different types of boundary layer trips that we're looking into and the different heights, their effects on the forces. So in figure 15 and 16, the effectiveness of the boundary layer trips can be examined by analyzing the aerodynamic performance of the airfoil with and without the boundary layer trips. Obviously, you just compare the baseline airfoils to the ones with these trips. And let me zoom in a little bit more so you can see a bit better. And if you're listening to this, you can always watch the video on Spotify and or our YouTube channel. And on our YouTube channel as well, you'll see some nice, fun simulations as well. So you will enjoy that. So the total drag on a typical airfoil mainly consists of pressure drag and skin friction drag. This is definitely true for a two-dimensional airfoil. For a three-dimensional airfoil at subsonic speeds, then we also have induced drag. And for a two-dimensional subsonic airfoil, it's pressure drag and skin friction drag. And skin friction drag is just the drag that arises from the fluid going over the surface. And pressure drag is the drag that arises due to the pressure differences over the surface. An additional drag here, though, is named the bubble drag, which will be added to when the LSB, the laminar separation bubble, is formed on the airfoil surface. And if you haven't listened to podcast 121 or quite a few of our other podcasts that cover LSBs, a laminar separation bubble is when you have the flow going over a surface, then it's laminar to begin with, then it detaches at a certain point. Then as it detaches, in that detachment zone, it actually transitions to turbulence, and then it reattaches and the flow is now turbulent. And in this detached zone, you have this recirculation bubble. This is termed an LSB or laminar separation bubble. So the purpose of providing a boundary layer trip is to control the formation of the laminar separation bubble and hence reduce the bubble drag. So the bubble drag here is just the additional drag that the LSB is forming. Now this is quite interesting because there are quite a few different angles that we can look at in terms of what drag the LSB is producing and or reducing. So if we have a surface and we have an LSB forming over the top, we have a recirculation zone in here. Now, the bubble obviously increases the height of this object by a certain amount, and that often results in more wake at the back. But inside the bubble, because the flow is actually moving upstream near the wall, we actually get this reverse drag. So it's actually a thrust. Now, this is a very small amount, but it's just interesting from a conceptual point of view that this little LSB can actually produce a little bit of localized thrust, and that does offset a little bit the drag this entire bubble produces. So I just wanted to cover that because it's a pretty cool little thing. So at the same time, the boundary layer trip will induce additional device drag due to the flow blockage, and an additional skin friction drag due to the turbulent flow resulting from the forced transition of the laminar flow to turbulent. So what this means is because we have this boundary layer trip upstream, we have the flow is laminar to begin with, and then as it hits here, it again becomes very turbulent, and then it goes downstream. Here now we have an increase in the skin friction drag. And this is because the flow near the wall is traveling at a faster speed. And this is one of the penalties that we have of using a boundary layer trip. Now, that's not necessarily a bad thing because if we do get additional benefits for the drag, that can offset this drag penalty and actually make boundary layer trips beneficial. In this case, potentially it doesn't, potentially it does. We'll figure out if it does or not. So to get a net reduction in the total drag for the tripped airfoil, the increased drag due to the boundary layer trip should be less than the reduction in the bubble drag achieved by eliminating the LSB. So in other words, the amount of drag that we are saving due to eliminating this LSB through using a boundary layer trip should offset all the drag increase that we get from the boundary layer trip. So let me cover quickly actually why a boundary layer trip would get rid of an LSB. As I mentioned, if we have an LSB over a surface, that is because initially we have a laminar flow. Now, if we don't have a laminar flow, an LSB cannot form because an LSB has to form because we have laminar flow, which then transitions when it detaches. So what we're doing is we're getting ahead of where the LSB would usually form. Let's say it forms halfway downstream here. And before that, we put the boundary layer trip. So the airflow hits here, then it turbulates. And as it reattaches behind the trip, it is now turbulent. Well, once it gets to the halfway mark, which is where the LSB would usually form, well, it's already turbulent, so an LSB will not form. So that's how it can get rid of LSBs, not to mention turbulate the boundary layer and transition it from laminar to turbulent. So what about for the first case of an angle attack of 4 degrees for this airfoil? Well, figure 15 shows the variation of the drag coefficient with trip height for the baseline and tripped airfoils. And these are for 2 different locations. Figure 15 does for location 1, which is 17% downstream from the leading edge. Figure 16 does location 2, which is 10% downstream from the leading edge. And you may not think this is such a big deal, but we'll get into in a second how it does actually have a very big effect, and we'll explain why. So figure 15 shows this effect of these different boundary layer trips at 17% from the downstream from the leading edge at 4 degrees angle of attack. The tripped airfoils show better performance compared to the baseline airfoil, and the performance varies with trip height and shape. So different boundary layer trips show improved performance at different trip heights. For example, the rectangular boundary layer trip has the maximum advantage of an 8.6% drop in the drag coefficient at a trip height of 0.3 millimeters at 70% downstream from the leading edge compared to the baseline airfoil. As the trip increases, like the height of the trip increases though, the advantage gets reduced. And beyond a height of 0.5 millimeters, the total drag coefficient becomes higher than that of the baseline airfoil for this rectangular trip. So it's only when the triangular trip is very small that we actually get drag reductions from it. Once it gets bigger, in fact, we can say pretty much for every boundary layer trip, as they get bigger, the drag coefficient increases and exceeds the baseline drag coefficient. It just depends on what shape the boundary layer trip has. So, for example, the right-angled triangle baseline trip, the right-angled triangle boundary layer trip, that is reducing the drag all the way up to 0.7 millimeters in height. Then above that, it increases it. Whereas for the rectangular and the isosceles triangle, both of them reduce the drag below 0.5 millimeters, but above that, they increase it. So there's a trade-off there. Now, for the angle, for when it's located at location 2, which is 10% downstream from the leading edge, they say that similar performance is observed for all kinds of trips when we are at this location. So most of the boundary layer trips will reduce the drag below 0.5 millimeters. There is the rectangular, the right angle triangle, sorry, that does increase the drag coefficient at 0.3 millimeters. However, that I reckon is probably an anomaly. Potentially not, I don't know, because the isosceles triangle also does it a little bit. But at 0.5 millimeters, they all reduce it somewhat, and then above that, they all increase it. So that's a very similar trend to the location 1, which was 17% downstream from the leading edge. They say that for these trip heights, the turbulence induced is insufficient to reduce the bubble drag. Trips at location 1, which is 17% downstream from the leading edge, show better performance over that of location 2, which is 10% downstream from the leading edge. So why is that? Well, the LSB is observed at a distance of 35% downstream from the leading edge on the baseline airfoil at an angle attack of 4 degrees. This is important, this location. The trip is located at a fixed distance of 17% or 10% downstream from the leading edge. This means that the trip at location 2, which is far upstream from the laminar separation bubble, compared to trip in the location 1, will not affect the LSB as much. So what this means is if we have the surface, whatever it is, and we'll usually get an LSB forming here at 35% downstream from the leading edge. If we put the trip at 10%, the turbulence that it creates by the time it gets to the laminar separation bubble region will dissipate and the flow will still stay laminar. If we put the boundary layer trip further downstream at 17%, now the turbulence that it produces is enough to stave off that LSB formation. Now, hopefully the boundary will transition to turbulence completely, but not necessarily. It really depends on the Reynolds number and the skin friction, and the roughness of the airfoil, and even the turbulence intensity. But ideally it would, but sometimes it doesn't. So this is where the location of the boundary trip does matter. If it's too far away from the LSB, it won't affect the LSB and we'll still get this increase in drag. If it's close enough, then we will be able to mitigate this LSB formation and we'll be able to reduce the drag of the airfoil. Now, what's more, if it's too big, like let's say it's too high, now we are getting so much turbulence that it's really overkill, and the benefits that we're getting from the boundary trip are not as great as the detriments that we are now inducing because of it. So that's a 4 degrees angle attack. What about at 6 degrees angle attack? Oh, sorry, let's talk about the lift to drag ratio. We're not going to go on 6 degrees yet, still sticking on 4 degrees. We'll get to 6 degrees in a second for all of us excited individuals. So the airfoil models with a boundary trip at location 1, so that's 17% downstream, have better lift to drag ratios for both the rectangular and isosceles triangle trips. And this is for a height up to 0.5 millimeters. And the right angle triangle has better lift to drag ratios up to 0.7 millimeters in height. So it's slightly better than both of the other two, the right angle triangle boundary trip. As the trip height increases, the performance degraded due to the higher total drag that all of the boundary trips induced. The total drag coefficient for the right angle triangle trip is higher than that for the other trips at 0.3 millimeters. And the same is reflected with the least value with the lowest lift to drag ratio. Also, the extended attachment region, because of the isosceles triangle trip at the higher trip height, affects the lift coefficient, and this resulted in a value of the lift to drag ratio closer to that of the rectangular boundary trip. So let's discuss this because it references the podcast that we just did 121. So the isosceles triangle boundary trip, because it doesn't have a sharp rear edge, what actually happens is that the flow takes longer to reattach, which is potentially counterintuitive, but in some ways it's not. So the right angle triangle and the rectangular boundary trip, because they have a flat back surface, the air comes down really hard and it just reattaches quite close to the back of the boundary trip. What this does is it allows the airfoil to produce more lift than the isosceles triangle one, because the isosceles triangle one has more of the airfoil is in this detached zone, which means that can't really produce much lift. That's why we get a reduced lift coefficient because of this isosceles triangle. That negatively affects the lift drag ratio. So not only is the drag important for this ratio, but also the lift is important. So if we are reducing the lift and or increasing the drag, the lift to drag ratio will reduce. And what we're seeing here is that for pretty much all boundary trips above 0.7 millimeters, we will get a reduction in the lift to drag ratio. The right angle triangle one is a little bit better, but generally speaking, it's not still perfect. And at 1 millimeters, there's a massive reduction. So the the baseline airfoil at clean has a lift drag ratio of 42.5, which is quite good. And the airfoils with boundary trips range from 27.5 to 37.5. So a massive reduction, almost like 40% in some cases. So that's not very good. They say as the trip height increases, performance degraded due to the total drag being higher. So they also talk about when the trip is located at 10% from the leading edge, which that's very upstream, as I mentioned earlier. When we have the boundary trip further away from the LSB, it's not as effective. But let's look at the lift to drag ratio here. So the rectangular trip has the highest lift to drag ratio of 47.5, which is 12% higher than the baseline. But for all other kinds of trips, the value is lower than that for the baseline. But when the trip height is 0.5 millimeters, all of them are now a bit higher. So there's some sort of funky thing going on here where if the boundary trip is too small at this 10% from the leading edge location, then it's not good. Like it's detrimental to the airfoil performance. When it's bigger, then it increases the airfoil performance until it gets too big, and then it reduces it again. So what is going on here? Well, for the very small case where the boundary trips are only 0.3 millimeters in height, this is likely due to just a localized increase in drag. It's not really turbulating the flow enough to make it completely turbulent, but there's this localized region which is just increasing skin friction drag and creating a lot of turbulence for no real reason. As we get to 0.5 millimeters in height, now we have a big enough boundary layer trip to be able to stave off this LSB. If we go even higher, well, now we're just introducing way too much turbulence and it's overkill, and we're getting a reduction in the lift to drag ratio, it seems. These are my general thoughts based on from what I can see, and it does make sense that this is what's happening. So this is sweet zone, where if you have the boundary layer trip of 0.5 millimeters, you'll get a increase in lift to drag ratio, but apart from that, it's bad at this location. You need to be further downstream near the LSB. So we talked about angles of attack of 4 degrees. Now let's move on to 6 degrees as promised. So figures 19 and 20 deal with this for the drag coefficient. The total drag coefficient for the airfoil with the boundary layer trips at 6 degrees for location 1, so that's 17% downstream from the leading edge, is shown in figure 19. And I should really say they should make location 1 location 2, because location 1 is 17% downstream, location 2 is 10%, but I would sort of expect location 1 to be 10% and location 2 be 17%. That's more numerically logical, but here it's not. Location 1 is 17% and location 2 is 10%. Anyway, let's just move on here. So up to a trip height of 0.5 millimeters at 6 degrees angle attack, all of the boundary layer trips produce lower drag than that of the baseline airfoil. The rectangular trip generates the least drag at the trip height of 0.3 millimeters, but with increasing trip height, the total drag coefficient of the right angle trip becomes lesser than that of the other types of trips. So that is interesting. So at 0.3 millimeters height, the rectangular boundary layer trip is the best performing in terms of the drag coefficient. But as we get higher in the boundary layer trip height, for some reason the right angled triangle becomes the best one. So there's a difference in flow physics going on there, which they don't seem to go into in this paper, but that's interesting for more further research, I guess. For the models with trips located at 10% from the leading edge, so location 2, which is in figure 20, the right rectangular trip performs better than the baseline until 0.7 millimeter trip height. The airfoil with other trip shapes performs better than the baseline airfoil for all the trip heights studied. The right angle triangle trip has superior performance over other models beyond the trip height of 0.7 millimeters due to its least resistance to the flow. And that's what we saw with the other location as well. So that's consistent between the two locations. And they said that is because the right angle triangle boundary layer trip doesn't produce as much resistance to the flow. So reductions in the net drag of the modified models results from the reduction in the bubble drag, which outweighs the induced device drag. As discussed previously, extended flow reattachment lengths of the isosceles triangle trip results in the long recirculation region and increase in the total drag of the model. Due to this reason, the total drag value of the model is closer to that of the rectangular trip, and trips at location 2 is far upstream from the LSB than that of location 1, but the distance is lesser than that for angles of attack of 4 degrees. So let's talk about this. So what they're referencing here is, as you have an airfoil or any surface really, as you continually pitch it at a higher angle of attack, the boundary layer, the LSB will move upstream. So if we had the airfoil at 4 degrees angle of attack, the LSB we know started at 0.35 downstream from the leading edge, 35% downstream from the leading edge. So these trips at 10% and 70% performed in a certain way. Now, if we increase the angle of attack to 6 degrees, the LSB will now be at a further upstream location, maybe let's say 25% upstream from the leading edge, or downstream from the leading edge, sorry. So now these trips are, relatively speaking, much closer to the LSB formation. So that means that the trips in location 2, which was only 10% from the leading edge, are not nearly as bad as what they were for angles of attack of 4 degrees, because now they're closer to the LSB, which means that you can use a lower boundary layer trip and still get very good performance. Say here, hence, trips at location 2 induces sufficient turbulence than that of location 1, but location 1 is still pretty decent compared to the angle of attack of 4 degrees. Let's talk about figures 21 and 22, which talk about the lift to drag ratios now. So effects of the trips on the lift drag ratios are presented in figures 21 and 22, and as in the case for the drag coefficient, the rectangular trip is effective up to heights of 0.5 millimeters, for location 1 and up to 0.7 milliliters for location 2. So again, location 2 is further upstream, and we need to have a bigger boundary layer trip just to get the performance we need. And then once you go above these heights, both or all boundary layer trips really degrade performance. Like at 1 millimeter heights, the lift to drag ratios are dropping by like 25, 30, 35%. So that's not good. We want to have the boundary layer trips smaller. This is akin to vortex generators, where vortex generators, we usually do get a drag penalty unless they are micro vortex generators, and this is akin to that. So they also cover angles of attack of 8 degrees, which are very similar to 6 degrees. They follow the very similar trend where the boundary layer trip at both locations perform a bit better than in the lower angles of attack because the LSBs are closer. And location 2, which is only 10% from the leading edge, is pretty decent still, the performance. So we're not going to go through those because we get similar trends here where when we have a small boundary layer trip height at locations very close to the LSB, they perform best. When we have moderate boundary layer trip heights at locations far away from the LSB, that's when they perform best. And then either side of that, we get reductions in the performance. But instead, we're going to look into the turbulent kinetic energy, because this is one thing that we don't really discuss too much, and it is quite an interesting phenomenon. So let me scroll down to the right figures and zoom out a little bit so we can see them. So we have the distribution of turbulent kinetic energy without and with boundary layer trips at angles of attack of 6 degrees for location 1, which is 17% downstream from the leading edge for the the right angle triangle trip. So this section illustrates the turbulent kinetic energy on the airfoil with and without boundary layer trips. Figure 27A shows the turbulent kinetic energy distribution for the baseline airfoil at angle of attack of 6 degrees. High turbulent kinetic energy is observed at a distance of 60% downstream from the leading edge, which represents the flow reattachment on the airfoil surface after the laminar separation. The flow is turbulent afterwards. So in other words, at the baseline airfoil, we have the flow separating and it's laminar, so we don't have really any turbulent kinetic energy. Turbulent kinetic energy is exactly that. It's kinetic energy of the turbulent part of the flow. And we can only really get that if the flow is turbulent. And we only get turbulence when the flow starts to reattach, so aft of the LSB. And when we do have the LSB reattaching, there is quite a lot of turbulent kinetic energy happening. So the flow is turbulent afterwards. The reattachment length after the trip aft reduces with increasing trip height, as shown in figures 27B to 27E. So this shows the right angle triangle boundary layer trip with increasing height. And as mentioned, like heights of 0.3 millimeters and 0.5 millimeters, the LSB is quite long still, but with 0.7 millimeters and 1 millimeter, the LSB is pretty much non-existent. Like the flow reattaches very closely to the trailing edge of the boundary layer trip, and there's a lot of turbulent kinetic energy, which indicates that the flow is now turbulent. So the LSB is pretty much completely eliminated, and that also is coincided with increases in the drag. But there's something else going on here, because I think that even at 0.5 millimeters and 0.3 millimeters, the LSBs probably aren't forming that coherently. So we're still getting massive benefits there. And when we get to higher boundary layer thickness, boundary layer trip heights, that's when we eliminate the LSB completely, but also just so much into the boundary layer that we are producing just too much turbulence, and it's not delivering any beneficial results now. So they're just too big. And they say here, from this figure, it can be seen that trips work as vortex generators, and the induced turbulence increases with trip height. So that's where I mentioned earlier that micro vortex generators, they are usually better at reducing the drag while still having beneficial effects on the flow in general. So I thought that was pretty cool looking at the turbulent kinetic energy there. So let's talk about the conclusion now. Let's sum this podcast up. The effect of the geometry, so the isosceles and right angle triangles, the location height of the boundary layer trips on the aerodynamic performance of the LSBs on an E216 airfoil are investigated using the transition gamma theta turbulence model, so RANS. The results are compared with that of the baseline and the rectangular trips from previous works of the authors. In the majority of the cases of the airfoils with the boundary layer trips, because of the additional turbulence, the LSBs get eliminated irrespective of the boundary layer trip shape. So the shape makes no difference to actually eliminating the LSB, but different shapes of the boundary layer trip, such as the isosceles triangle and the right angle triangle, have no specific advantage over the rectangular triangle trip. In the case of the rectangular trip, the leading edge is normal to the flow, and hence it induces sufficient mixing even at low trip heights, so up to 0.5 millimeters, and hence shows better performance. For other kinds of trips, the leading edge is inclined to the flow direction, and hence the device drag is less, but at the same time, the induced turbulence is also less at the lower trip heights compared to the rectangular trip. So what that means is the rectangular trip is more effective at low heights because it is so blunt, whereas the other objects, because they are much more gentle in the leading edges, they need to be bigger to get the same kind of turbulence production. The required mixing is achieved only at higher trip heights for these boundary layer trip shapes. There exists an optimum trip height and location for each boundary layer trip at every angle of attack to achieve the optimum improvement in the aerodynamic performance of the airfoil. Highest improvements in drag were 17.41% and corresponds to the drag ratios increases of 10.86%. They're obtained for the isosceles triangle at location 2, which is 10% upstream from the leading edge, 10% downstream from the leading edge for angles of attack of 6 degrees over the baseline airfoil. So even though the isosceles triangle was not necessarily better among a broader range of flow conditions, the maximum improvement was attained by that trip at these specific locations and heights. So that's the end of this podcast. Make sure to like, subscribe, and if you want to get better at theory and or CFD yourself, so we've gone through theory here in podcast 121 and 122, and we've gone through CFD as well. Check out our course in the description. We go through courses there about CFD and theory. And if you want to get your experiments to be 2 to 4% more accurate, so all your results that you get to be far more accurate, check out that Mr. Hawk. The reason why it makes your experiments 2 to 4% more accurate is because it's an instrument that accurately measures the density of air. The density of air changes every day by 2 to 4%, and this is very normal. And between weeks, seasons, and months, it increases even more, like 15% is normal. So the density of air is changing every day from hour to hour, day to day, week to week. You need to measure that in order to be able to take that into account for your experiments. If you don't do that, you get that error in your experiments, which most experiments unfortunately do have. The Atmosphere Hawk gets rid of that experiment for you, that error for you, sorry. So your experiments are more accurate, and that means you don't have to do as many experiments. And that also means that your CFD is more accurate as well, because your validation data that you get from your experiments are now lining up with your CFD because you're using the right densities. So this is the example here. If you have your CFD and you're running it at a density of 1.2 kilograms per meter cube, but your experimental data that you got for validation, the density of air ranged from 1.15 to 1.18, or regardless of what you use, is still wrong because the CFD density is different. So you can't expect to have the same results. So your validation is going to be wrong, and you have to try to force it, which is obviously bad research practice. So the Atmosphere Hawk gets rid of that error for you and makes your experiments much easier, makes it much better for your CFD as well. Check that out, and I'll see you in the next podcast. Peace out, amigos.